like the real ratings that are.
All right, so we are switching gears just a little bit. We are going to start talking about radioactivity, which, by the way, is my favorite topic, so I get a little energetic. But anyhow, honestly, this is probably going to be a easy and a short unit. It's only 2 chapters versus the 6 we did in the first unit, where I'm guessing that we're going to test next Thursday, because there's only 2 chapters of material. There's only 1 lab, not next Tuesday, next Thursday. Is that what I said?
Yes.
Next Thursday. Your test or this will probably be next Thursday. That gives us 3 days. There's only 2 chapters and 1 lab, so I don't know if I can spread it out that much more than that. But anyhow, and I feel like this has a more focused amount of information as opposed to so much broad information. Okay, so first of all, let's just review. We just took a test over this, so we should all know this, but what is an atom made out of? Atoms are made out of 3 particles. We have protons, neutrons, electrons. Protons plus neutrons are located in the nucleus, right? The electrons are outside the nucleus. The number of protons determines the element. So, for instance, sodium always has 11 protons. If you gain or lose a proton, you completely change the element. You can gain or lose electrons. You can gain or lose neutrons, but the protons have to stay the same. Okay? The neutrons plus the protons gives you the average atomic mass, which is what's listed on the periodic table. But if we look at the periodic table, they're decimals, right? Can we have 0.9815 of a proton or neutron? No. So why are those not whole numbers up there? Why are those crazy decimals? Anyone? They're the average. That number is up there average. If I take an average of your guys' test grades, I'm probably not going to get a whole number. I'm going to have to round, right? Okay, same thing up there. That's the average. Not every single atom of oxygen is identical. Not every single atom of sodium is identical, just like no one in this room is identical. So therefore, those masses listed up there are actually the average. Okay? Okay. Now, the important part of this chapter is neutrons. Last chapter, we focused a lot on electrons, right? We focused on bonding. We focused on covalent bonding, sharing, stealing electrons, right? This chapter focuses a lot on neutrons. Okay, that is what makes things radioactive. The number of neutrons can vary without greatly affecting the nature of an atom. Sodium. Some sodium atoms have 11 neutrons. Some sodium atoms have 12. It's still sodium. They still do the same thing. It's not a huge deal. Okay, the number of neutrons can vary relatively easily. Which leads us to what an isotope is. Okay, does anyone remember what an ion is from last unit? An atom with a different charge, right? Had to lose or gain electrons. Well, an isotope is an atom of the same element that has a different number of neutrons. In Greek, an isotope means in the same place. So they're the same place on the periodic table. They just have a different number of neutrons. Elements will have the same number of protons, but they go through various processes to possibly change the number of neutrons. Okay, so just like last unit, we learned how to write the charges, right? We learned that when we were trying to talk about an ion, we would put the charge as a superscript up here in the right-hand corner of the symbol, right? Right. Well, now that we're starting to talk about isotopes, we need to also add a few things. So over here on the top right as a superscript, you will see the mass number of 24. That is a whole number. So if I look at the periodic table and I see sodium is 22.989, am I going to put that on my mass number spot? 22.898. Am I going to put that? What am I going to round it to? 22.9 gets rounded to 23. If we look up their magnesium, which is what I have the example on the slide, magnesium has a mass of 24.305. I'm not going to write 24.305 because a mass number needs to be a whole number, so I have to round it. 24.4 rounds down to 24. So these numbers are always whole numbers. And then the subscript on the left is a 12, and that's telling you the number of protons, identifying the element. Now, if you look in your book, I'm not exactly sure, but on your book, he puts the mass in the top right as a superscript.
Yes, he does.
That's wrong. I'm not really sure why he did that. But if we were to put the mass number there, we would have no place to put the charge. So everybody either write in your book, for those of you who like to highlight in your book, for those of you who like to take notes, make a note to say that the mass number is actually on the left side, not on the right side. It's still a superscript, but it's on the left side of the element, just like I have seen here. Okay, I'm not really sure why the author did that incorrectly, but so this is magnesium. Magnesium has a mass of 24. He has an atomic number of 12, and he has a charge. This one has a charge of 2 positive. Okay, so from all this information, we can figure out number of protons, the number of neutrons, the number of electrons. All right, so let's look at an example of an isotope. Let's look at hydrogen. Hydrogen has 3 known isotopes, which means hydrogen exists in 3 different forms. So we have protium, deuterium, and tritium. Okay, they're all hydrogen atoms. They all have 1 proton. The protons are the red circles. But if you notice, protium, does he have any black circles? No, that's because protium, which is the guy on the periodic table, has no neutrons. The hydrogen listed on the periodic table has 1 proton, 1 electron, and that's it. Okay? Deuterium, however, he has a black circle in the center, correct? This guy has gained a neutron from somewhere, and so he has 1 proton, 1 neutron, and 1 electron. Tritium, the third one, has 2 black dots. He has 1 proton, 2 neutrons, and 1 electron. The only thing that's changing as I go up from the different isotopes is the number of neutrons, right? Each one of them has 1 red dot. Each one of them has 1 blue dot. The protons and electrons are identical in isotopes. The only thing that's changing is the number of neutrons, which affects its stability. But let's look at the third bullet point. If we look at the periodic table, it says that hydrogen has an average atomic mass of 1.00794, which means that hydrogen on the periodic table has no neutrons, right? Because remember, the mass is telling you protons plus neutrons. Well, if your mass is 1, you only have a proton, correct? So let's try to figure out who's more abundant. If the average is 1, which means you only have 1 proton, then which of these 3 guys do you think is the most abundant? Protium, the first one. The first one's most abundant because a mass of 1 is closest to 1.01, isn't it? As opposed to 2 versus 3. So when you're trying, and there probably will be several questions on your test, and there are a few on your homework, when it says which of these isotopes is most abundant, all you have to do is look at the average atomic mass and which one of these is closer. So like, for instance, oxygen, its average atomic mass is 15.9994. Which isotope of oxygen do you think is most abundant? 16. Okay, if we look at, let's do a hard one. Can't find a hard one. Boron has an average atomic mass of 10.8. Which isotope do you think is going to be more abundant? 11. Okay, there's more boron 10s because 0.8 is a lot smaller than 0.9994, right? But 11 is still most abundant. So all you have to do is look at that number, round it, and you can figure out which one is the most abundant. Okay. Let's look at another example. Let's look at carbon. Carbon's important. This is how we date. This is how archaeologists can determine how old artifacts are. They use carbon-14. Okay. Carbon also has 3 known isotopes. They all have 6 protons. The only difference in these isotopes is the number of neutrons. Carbon-12, which is 98.9% abundant, so the majority of carbon in our world is carbon-12. It has 6 protons and 6 neutrons. Carbon-13 has 6 protons but 7 neutrons, so it has an additional neutron. And then carbon-14, which is again how we date artifacts is less than 0.1%, and it has 6 protons and 8 neutrons. So if we're trying to determine which one's the most abundant, on the periodic table, carbon's average atomic mass is 12.011. That's closest to 12, right? Well, I just told you carbon-12 is 98.9%, so that's pretty accurate, correct? All you have to do is round, and you can make a pretty good guess. But did you guys notice how when we were talking about hydrogen, I gave them names? Protium, deuterium, tritium. Did I do that here? No. Okay, hydrogen is the only element that has specific names for its isotopes. All the other isotopes, I mean, if you think about it, there are 118 elements on the periodic table. If each one has 3 isotopes, that's a whole lot of names for everybody to try to remember, correct? So instead of naming different isotopes, they just came up with a different way to write it. So all we have to do is we write their name and we list their atomic mass after their name. So if we look at the first bullet point, we see carbon-12. I'm talking about carbon with a mass number of 12, which is the person on the periodic table, right? If I'm talking about carbon-14, that's not the same guy on the periodic table, right? Carbon-14 has an additional 2 neutrons. Carbon-12 has 6 protons, 6 neutrons. Carbon-14 has 6 protons, 8 neutrons. Same element, they're going to behave relatively equally. The only difference is the number of neutrons. Again, to find the number of neutrons, all you have to do is take your mass number subtracted by the number of protons. So let's do an example really quick. I think that was probably just a side note. Let's do an example. Let's do, just to give us a little bit of practice, let's do aluminum. Okay, so if I look at the periodic table, aluminum has an average atomic mass of 26.9. What should I round that to? 27. He has an atomic number of 13. Okay, what is the atomic number telling you? How many protons? So aluminum has 13 protons. To figure out its neutrons, we are going to just subtract the two. So we're going to do 27 minus 13, which gives you 14 neutrons. Now, for the most of the elements that we're going to be doing, a lot of times the neutrons are 1-to-1, which means if there's 1 proton, there's 1 neutron. If there's 2 protons, 2 neutrons. For the elements that we deal with usually in class, they usually have a 1-to-1. As you start getting farther and farther down the periodic table, the ratio starts to get a little bit more skewed, which is why those elements tend to be a little bit more radioactive. But let's look at a different set of isotopes. Let's look at chlorine. Okay, chlorine exists in 2 isotopes. They exist as chlorine-35, and they exist as chlorine-37. So, first of all, how many protons does each of these have? 17. This number right here is telling you protons, so we have 17 protons. How many neutrons does each have? How do I find the neutrons again? I subtract the 2, and honestly, the way these have them set up, just set it up as an subtraction problem. Put your bar down here, put a subtraction sign, and subtract them. 35 minus 17 gives you 13, 18. 18. Math today is bad. Subtract them, so this one's going to give you 20. Okay. Now this is the hard question. The hard question says which one is more abundant and what percentage do you think each is found? So let's go with the first one. We need to figure out which one's more abundant, aka which one is closest to the average. So the average is 35.45. Is that closer to 35 or 37? 35. 35 is more abundant. Well, let's try to figure out the percentages. Okay, so when I try to figure out the percentages, I just kind of look at it like a number line. Let's put 35 down here. Let's put 37 over here. Smack dab in the middle is 36, correct? But there is no isotope 36. There's only chlorine-35. There's only chlorine-37. Well, the average mass is right there, 35.5, correct? So if 35 is more abundant, if you just had to take a stab at the percentages, that looks like fourths to me, doesn't it to you? 1, 2, 3, 1, 2, 3, 4. It looks like fourths. So, if 35 is more abundant, what do you just take a guess at the percentages? What do you think? 75% is going to be chlorine 35, and 25% is going to be chlorine 37. And I'm not going to make you guys actually do the algebra, but you'll probably have to make a guesstimate. I'm not going to give you hard numbers. I'm going to give you one that's pretty straightforward. But just think about, I always just kind of draw a number line, divide it into fourths, divide it into fifths, maybe even eighths, and then kind of just see what the percentages are, okay? All right, so let's spend a little bit of time talking about neutrons. Like I said, in the smaller atoms, basically 1 through 20, for the most part, we have a 1-to-1 ratio. Occasionally, it'll be 6 versus 7 neutrons, but that's still, if we rounded, that'd be pretty close to a 1-to-1 ratio. However, as the atoms get bigger and bigger, sometimes the ratio can double to a 1-to-2 ratio, which means they have twice as many neutrons as they have protons, which is bad. Okay? Basically, the reason why our neutrons double is because it's kind of like they try to keep the protons from fighting. Now, if you remember, protons are positively charged. So the more protons you try to pack into a small area, the more they're going to repel each other, right? So those neutrons kind of serve as glue to hold all those protons together that are repelling each other. However, there's a limit to how much you can hold. It's kind of like this room. There's a limit to how many people I can shove in this room, correct? Now, I could keep shoving, and I could keep shoving, and I keep shoving, but people start to get more and more unhappy and more uncomfortable. Same thing. The more protons and more neutrons you try to shove into the nucleus, there creates some sort of issue. So the only thing we can change is neutrons. So if there's too many neutrons or there's too few neutrons, it leads us to something called a radioactive element, which I'm sure you guys have all heard of before, right? Okay, so radioactivity, again, are these atoms that have too many or too few neutrons, so they're unstable. Too many things have been packed into the nucleus. This was actually discovered accidentally in 1896 by Antoine Becquerel. She was actually studying fluorescence, which for those, that's when something kind of glows on its own. Do you know what I'm talking about? She was studying that. And she accidentally, she had some film, undeveloped film. She had some film in a drawer, and what ended up happening is she put a piece of uranium in there, and she shut the drawer, and she went on with her work. She came back and she went to develop her film, and what had happened is the film was just fog. So she's kind of like, because if any of you ever seen film that's been exposed to light, if you accidentally expose your film in your camera to a light, which most of the time we have digital cameras now, so nobody does film anymore. But if you expose your film to light when you're trying to open it, it ruins all of your pictures. Because if you expose, that's how pictures work. You expose light to film really quickly, and it kind of burns it into the film. So she said, well, I didn't expose my film to light, so what in the world happened? So, of course, she was a scientist, so she did it again. She put the film in there with uranium, and the same thing happened. Well, that didn't really help her much. So what she did is she took a key, which keys are made out of metal, correct? And she set it down on the film, and then she put it in the drawer. And what happened was the key was built into the film. So it's like light was hitting every piece of the film except where the key was. So then she was like, well, something was hitting these, but it couldn't penetrate the metal. So they must be emitting some sort of rays of some sort, like light. Okay, so that was her discovery. But that probably it took me 5 minutes to explain the story, but that probably took her months and months and months of research to figure out. So what actually happened is Pierre and Marie Curie, which you guys have all heard of Marie Curie, haven't you? They took her ideas and they kind of ran with it. They actually discovered that all uranium and thorium compounds will do the same thing when they're exposed to film. So both of these compounds are emitting some sort of rays. Okay, they termed this radioactivity, and they also discovered polonium and radium, which are elements that are only made from uranium and thorium. If you don't have uranium or thorium, you're not going to have these elements. Ironically, Marie died of a blood disease, possibly brought on by her work with radioactivity, and her husband actually died in a car wreck, but they believe that he got in the car wreck because he was suffering from radiation poisoning. So, did they know radiation was bad? No. They didn't understand that that can affect your body and that can cause bad health effects, but the benefits of radiation or of any scientific discovery are usually discovered before the dangers are, which is why we have clinical trials for medications before they're approved by the government and so on and so forth. Okay, so radioactivity, when there are too many or too few neutrons, it can make the nucleus unstable. So it's like, remember how everybody wants to be like a noble gas? Okay, well, everybody wants a 1-to-1 ratio too. Everyone wants 1 proton to 1 neutron because that makes everybody happy. It gives everybody a partner. So isotopes that are unstable are also radioactive, and these are called radioisotopes. So carbon-12 and carbon-13 are pretty stable. They have a pretty close to 1-to-1 ratio. But then carbon-14, however, throw an additional neutron in there, it kind of throws off the balance. And this one is radioactive, which means that he's going to try to do anything he can to become a 1-to-1 ratio. Okay, nuclei that are too big also contain more than 82 protons. So if we look at the periodic table, lead is number 82. Okay, any element past lead, for the most part, is radioactive, which means it emits these rays that they were studying. It emits some sort of radiation. It is unstable. It is going to react quickly with somebody else. It is created through a radioactive process, etc. All right. However, some elements are more radioactive than others. So carbon-14 is a radioactive element, but we use carbon-14 all the time for dating. So it doesn't seem like it's very harmful, correct? However, X-rays, you go to the doctor, you have to get an X-ray. That type of radiation is very harmful. That's why X-ray techs always stay in another room or behind a lead screen because they don't want to be exposed to those rays every single day, patient after patient. Radiation is not all created equal. So like bismuth 109, this is virtually stable. It will take it 1.9 times 10 to the 19 years for half of the sample to decay into something else. So this decay process in which you're turning one thing into another, this is what radiation is. This is what the radioactivity is. In this process, it releases some sort of energy. But if it takes that long, 1.9 times 10 to the 19th, that's 19 with 18 zeros after it. I don't even know what that is. It's way past trillion, correct? If it takes that long for half of a sample to decay, is it going to be releasing energy very quickly? No. So is it radioactive? Yes. Is it creating radiation and is it releasing it? Yes. But the amount that it's releasing is so small and spread out over so much time that it's not really harmful. Okay? All elements between number 83 and number 92 are byproducts of uranium and thorium. Does everyone know what a byproduct is? What's a byproduct? Okay, a byproduct is something that is produced through a reaction. So uranium is very reactive, okay? It's radioactive, which means it is going to try to do stuff to its nucleus to make it more stable. Well, in the process, it is going to transform its thing into other elements. Well, all the elements between 83 and 92 are involved in this process. They start out as uranium, they start out as thorium, and they are converted into these other elements. So they don't occur all by themselves. Okay, all elements beyond uranium are radioactive to not be found in nature. They are man-made, which means through our radioactive processes, while we're trying to harness this energy and use it for our good, we are also making them. And since they are not found in nature, do you think we can find an average atomic mass for them? No. So we guesstimate. So if we look at the periodic table, if we look at all of the elements towards the bottom half, do you see how the masses are in parentheses? Do you see how those masses back there are in parentheses? Towards the bottom of the periodic table? That's telling you that those are man-made products. That's telling you that they don't exist naturally. So they don't have an average atomic mass. We just guesstimated on their mass. So we've been talking about radioactive, but what is it? Radioactive elements eventually will undergo some sort of change. And we call this a nuclear change because we're talking about a change in the nucleus. We're going to add or take away neutrons. Okay, atoms are going to rearrange themselves to form new compounds. The original nucleus is called the parent nucleus, and the resulting nucleus after the change is often called the daughter nucleus. So what it starts out as, the radioactive nuclei, is the parent. What it changes into is the daughter. And no, we don't talk about sons. They're just called daughters for some reason.
I love how it says, at least on Earth,
They're not what?
it says all elements beyond uranium in the periodic table are radioactive and thus not to be found in nature, at least on Earth.
Okay, well, not all radioactive decay is the same. There are actually three main, and we're going to talk about a few subset ones, but there are three main types of decay. And when I say decay, I'm talking about a radioactive process in which one thing is changing into another. So just like when we were talking about decomposition reaction, we took one thing and we changed it into two separate things. Same thing here. Radioactive decay is when I take one atom and I change it into two separate things. Okay? Some radiation is more harmful than others, and they term this, basically when we're talking about how harmful the radiation is, we're talking about how much it can penetrate a surface, or what type of surfaces do you need, your skin, the piece of paper, lead, so on and so forth. So, some rays can be stopped with a piece of paper. So you can just hold it up and be like, don't hurt me, and you hold up a piece of paper and it'll stop the rays. So is that very harmful radiation? No. Some can only be stopped with feet of lead. So this would be like the bomb shelters people built when Russia was going to bomb us, right? They would build it with really thick lead around it. And this is what we did with Chernobyl, with the big explosion and the radiation was released. They actually covered it in lead and concrete to try to contain the radiation. And some can be bent by an electric charge or a magnetic field, which means that some of them have a charge to them. Just like electrons and protons have a charge, sometimes these rays have charges. So there are three distinct types, so we're going to talk about them, and they're all given a Greek letter. There is alpha, beta, and gamma. Now, you might want to get a little bit of practice at drawing these. They're Greek letters. Alpha basically is the fish symbol, right? So just go like that. There's alpha. Beta, to me, looks like a bee with a tail. So I draw it like that, has a tail. And then gamma is kind of like a curvy Y. So I just kind of draw a Y with a loop at the bottom. Alpha, beta, gamma. Okay, so let's talk about the first one. Let's talk about alpha. Now, alpha and beta rays are particles and not energy, which means that when we do this type of radioactive decay, we're actually breaking off matter. Because remember, matter and light are two different things, right? Matter and energy are two different things. So alpha and beta rays are particles, which means they're matter that we can physically measure somehow. Okay, so the first one is alpha. These are the least harmful penetrating, which means these are the ones that can be stopped by a piece of paper. These are not going to hurt you very much. These are also attracted toward the negative plate, which implies that they have a positive charge. Okay, if they're attracted towards the negative side, they're going to be positively charged. The second type is called a beta. These are a little bit more harmful because they need several centimeters of wood in order to stop. So this would be like the walls of your house would stop beta rays. Okay, a door would stop a beta ray. Okay, the table would stop a beta ray. You need about 5 centimeters of wood, and you're going to be safe from it. So it takes a little bit more than a piece of paper, but still not quite too bad. And these are actually attracted to the positive plate, which means they are negatively charged. So alpha are positive, beta are negative. And then the third kind is called a gamma ray. And gamma rays are actually a form of light. So they are a type of energy. So is it matter that we can physically contain exactly? No. That is why these are so dangerous. It's not exactly something we can hold on to and contain. It's just light. It's hard to contain light, isn't it? Okay, so these are the most harmful. This is what, when we think of radiation poisoning, when you think of radiation being released, when you think of nuclear disasters, this is the type of energy you're thinking about. This is the type that is very harmful, the type that causes lots of sickness, so on and so forth. In order to protect yourself from gamma rays, you need 6 feet of lead or concrete, which I don't know about you guys, but there's not a whole lot of buildings around that contain 6 feet. I mean, I'm 6 feet tall, so you would need a wall as thick as I am tall in all 4 directions in order to protect you from gamma rays. These rays are also not attracted to either charge plate. They just pass straight through, which implies that they have no charge, which makes sense because they're not matter. They're just energy. So if you don't have protons, neutrons, electrons, you can't be charged.